Welcome to The Explainer. Today, we're tackling something that is literally a life or death topic for the future of healthcare. We're talking about interpreting AI models for medical decision-making. We're going to do a real clinical dissection of how these systems work, taking all that complex data science and translating it into transparent, actionable clinical insights. Okay, let's dive into this. Imagine for a second you're right there in the emergency room. A predictive algorithm suddenly alerts you that your patient is high risk and recommends a pretty aggressive intervention. But when you ask the system why, it can't tell you. It just spits out a prediction. Would you actually trust that medical diagnosis if you couldn't see the reasoning behind it? This is exactly the profound and honestly very practical dilemma we face when we try to use opaque neural networks in healthcare. There's a great quote here that hits the nail on the head. Transparency supports accountability. Understanding why builds trust and enables meaningful oversight. In these life-or-death clinical situations, explainability isn't just some nice-to-have bonus feature, it is an absolute necessity. I mean, if a model is making a decision that affects a patient's life, we have to be able to trace and audit that logic to make absolutely sure it aligns with sound medical principles. To get there, we'll be looking at, first, the medical AI black box, then the anatomy of a decision tree, how we calculate clinical certainty, a real-world case study on antibiotic prescribing, and finally, how AI balances with clinical judgment. Let's start with Section 1, the medical AI black box. So we're constantly hearing about deep learning neural networks, right? And while they are undeniably powerful, they act as these mysterious black boxes. We literally can't see how they think. You put data in and boom, you get an answer out. But on the flip side of that, we have glass box models, specifically decision trees. These algorithms are amazing because they mirror natural human decision-making. Unlike a doctor's notoriously messy handwriting, they give us this clean, transparent, step-by-step logical pathway. It closely resembles our own clinical triage processes, which means domain experts can actually validate the reasoning. Moving on to Section 2, Anatomy of a Decision Tree. First up, we need to define our primary tool here, which is CART. That stands for Classification and Regression Trees. It's an algorithm introduced by Leo Breiman that builds binary decision trees by repeatedly splitting a dataset into two subsets based on the most informative feature. And what makes CART so incredibly valuable in a clinical setting is its versatility. It can handle continuous numeric values, like a patient's age or their lab results, just as easily as it handles categorical data, like a discrete diagnosis. It helps to think of the CART structure like a standard triage sequence. Step 1 is the root node. This represents your entire patient cohort right at the beginning, before any decisions are made. Then we move to Step 2, the internal or decision nodes. This is where specific tests happen, like checking if a lab value exceeds a certain threshold or if a specific symptom is present. Finally, following those branches down brings us to Step 3, the leaf or terminal nodes, which deliver the final diagnosis, prognosis, or that predicted numerical value.
Which brings us to Section 3, Calculating Clinical Certainty.
Now, the type of tree you actually build depends entirely on your clinical target. We use classification trees when we're trying to predict discrete, categorical diseases. For instance, making a sharp distinction to identify a tumor as benign versus malignant. On the other hand, we use regression trees when we're predicting flowing, continuous, numerical metrics. Things like forecasting a patient's expected length of stay, predicting their blood pressure, or estimating total healthcare costs.
But how does the algorithm actually evaluate a split in a classification tree? Well, it uses a mathematical metric called Gini impurity. Gini impurity basically measures how mixed the classes are within a given subset, so it's estimating the probability of an incorrect classification. In a clinical context, you can just think of impurity as clinical uncertainty. A really effective split, much like a highly sensitive medical test, reduces this uncertainty. It filters out the noise and creates purer, cleaner patient cohorts as you move further down the tree.
Let's see this in action in Section 4, Case Study Antibiotic Prescribing. Now, what's really interesting about this slide is our objective. We want to analyze the specific factors associated with a physician's rate of prescribing antibiotics for viral respiratory infections. Our ultimate goal here is to identify the most effective location and demographic to target an intervention against overprescribing, specifically at Boston Medical Center. Let's put on our chart review hats for a second and follow the branches of this regression tree, which visually breaks down those prescribing rates. We start at the top root node, and you'll see the first major split is based on whether the patient has private insurance. As we follow the left and right branches down, the data gets further split based on whether the provider specializes in family medicine and also the race of the patient. Looking all the way down at the terminal leaf nodes at the bottom, we uncover some vital key findings. For privately insured Black patients, the average prescribing rate is 48%. However, for patient visits without private insurance, where the physician is a family medicine doctor, the average prescribing rate jumps up to 54%. So what does this tell us? It shows that among those without private insurance, seeing a family medicine doctor raises the average provider prescribing rate by approximately 10%.
And of course, an observation like that naturally sparks a follow-up question, right? What patient characteristics actually drive the choice to see a family medicine doctor in the first place? To figure out if patient demographics are driving these prescribing differences, we need to totally shift our approach. We're going to transition from our regression tree, which was predicting a continuous rate, over to a classification tree predicting a binary category.
And this brilliantly illustrates that shift. We are now predicting whether a patient uses a family medicine practitioner based on race, age, and insurance status. If you look at the bottom left leaf, we can see that young, Black patients make up the largest share, with 42% having a family medicine physician. This demographic insight gives us a much clearer picture of the actual patient population that's driving the prescribing patterns we just observed.
However, we do need to point out the 24% misclassification error rate for this family medicine model. This is a really crucial reminder for all of us. While these algorithmic tools are fantastic at generating hypotheses and pointing us toward potential public health interventions, they are absolutely not definitive proof. They still require further empirical research and human validation before we'd ever implement widespread policy changes. Which brings us to our final section, AI and clinical judgment.
Just like any medical tool we use, CART definitely has its clinical blind spots. A major limitation is overfitting. This is where the tree grows way too deep and becomes overly specific to the training data, meaning it completely fails to generalize to new patients. It's also sensitive to outliers and something called feature masking. To combat this, we rely on techniques like cost complexity pruning. It's actually a lot like pruning a physical tree in your yard. You trim back the overgrown, unnecessary branches so the tree yields better, healthier fruit. Or, in our case, better clinical results.
Another really clever feature CART uses to handle missing values is called surrogate splits. Put simply, if a lab result is missing, the algorithm just finds the next best proxy. It uses other features that mimic the primary partition as closely as possible. This is great because it captures latent relationships, ensuring that highly predictive but correlated features are still factored into the calculation, even if one happens to be masking the other.
Ultimately, we have to draw a line between machine learning trees, which just automate predictions directly from data, and operational decision trees. Operational trees are where the real power lies for improving patient care, because they guide human execution at scale. They allow us to take tribal clinical knowledge and formalize it, embed compliance directly into our workflows, and ensure consistent evidence-based triage across an entire healthcare organization.
So, the crucial point is this. Formalizing clinical intuition requires human-in-the-loop oversight. Decision trees do not and should not replace clinicians. They simply guide them in an auditable, transparent way, allowing medical professionals to actually review the branches and validate the machine's logic against established clinical guidelines.
I'll leave you with this final thought. As you continue to integrate predictive tools into your healthcare practice, ask yourself, do your clinical models formalize intuition into auditable, transparent logic, or are you still blindly trusting the black box? Thank you so much for joining me on this explainer. I really hope this helps you navigate the complex but totally fascinating future of clinical AI.